Hello, everybody, and welcome back to another lecture in Geography 340 Climatology. I am Dr. Zach Hilgendorf, and today we're going to be talking about atmospheric pressure and wind. This is really going to start setting up the discussion and the topic for our next lecture, which is going to be on global cycles and global patterns of pressure and wind. Things like the Hadley cells and the intertropical convergence zone, and what these things mean and what's really driving them. This is all going to lead into a complementary topic on global ocean circulation, things called gyres and ocean currents. So let's start off with atmospheric pressure and wind. So atmospheric pressure, as you may recall, is the average force per unit area exerted by randomly moving gas molecules bouncing off of a surface. We typically think of this as the force exerted on the surface of our planet by our atmosphere. We typically look at this, as we may recall, in units like pounds per square inch, newtons per square meter, or Pascal. And if we have 100 newtons per square meter, we have a hectopascal or a millibar that we can convert to. So we can think of these particles and molecules of air bouncing around chaotically, like we see here in this example. That pressure can build up based off of how dense these air parcels are, how much weight is being exerted on the overlying surface. So what determines air pressure? Well, air pressure is calculated through the ideal gas law, which says that pressure here is equal to rho RT, where rho is density in kilograms per meter cubed, T is temperature in Kelvin, and R is the specific gas constant, or 287 joules per kilogram per Kelvin. As temperature and density fluctuate, we see changes in the overall pressure. This moves our needle up and down. So, of course, in the free atmosphere, without these constraining boxes and perfect systems, it can be difficult to determine air pressure in the free atmosphere. However, we can easily arrange or rearrange the ideal gas law. So we think of it in terms of rho, or density, equal to pressure divided by the specific gas constant times temperature. It can be a bit easier to get at what these changes and differences are as we move up and down in our atmosphere. So let's look here. So what is pressure at sea level? Do we recall what it is? Well, given that it has the most greatest amount of air and atmosphere over top, we have a high pressure, so 101,325 newtons per meter squared. We typically also think of this as how much pressure is being applied to a 1 by 1 meter square area. We typically look at this and can use 101,325 pascals, as we talked about in a few slides ago, or 1,013.25 hectopascals, or 1,013.25 millibars. They're all the same thing, and you can just convert between them. Now, if we increase our altitude from 0 kilometers to 5 kilometers, we basically decrease our pressure to about half of the atmospheric pressure and density than at sea level. This averages about 540 millibars. Let's jump up a little bit more and then rise up to 10 kilometers. We drop to about a quarter of the atmospheric density and pressure for that same square meter. We get to about 264 millibars. If we jump up to 15 kilometers, you drop to about 12% of the atmospheric pressure and density, drop to about 120 millibars. Here we can see a graph of standard atmospheric pressure versus altitude. You want to use this graph in the next couple of slides, so go ahead and pause the video and screenshot this, or use the PDF file with the slides on Canvas for reference. This trend actually closely mirrors that of atmospheric density versus altitude, which we can see here. So what is atmospheric density of air, and what is the atmospheric density of air at sea level? Well, using our reorganized ideal gas law, where density is equal to pressure divided by the specific gas constant times temperature, we can figure this out. Of course, we're also going to need to think about temperature and what temperature is at altitude. So this is a bit tougher because, as we learned when we looked at the structure of our atmosphere, temperature changes depending on where you're at in our atmosphere. It can increase, it can decrease. In the troposphere, we generally see decreasing temperatures with atmosphere or with altitude. But then we have the tropopause, the stratosphere, the mesosphere, all of the pauses associated therein. It can be a bit tough. So NASA's provided some equations to help kind of sort this out from a meteorological sense. So we see here, the base equation is 15 minus 0.00649 times h, where h is that altitude value. And then to convert it, those are in degrees Celsius within the brackets. To convert it to Kelvin, that's why we have that other portion at the end there, adding 273.15. That's to get it from Celsius to Kelvin. So we look here, we know, or we're trying to find density. So rho is equal to 101,325 pascals, as we may recall from our previous slides or from using the pressure graph. Divide that by 287 joules per kilogram per Kelvin times 288.15 degrees Kelvin. Did you get the density of air equal to about 1.225 kilograms per cubic meter? Hopefully. That is kind of standard density of air that we look at, kind of take as standard. You usually think of standard temperature, density, and pressure. All of these things fluctuate, but if we look at averages, 1.225 kilograms per cubic meter is basically the average density of air at sea level. We can use our graph here as well. You can find that same thing. All right, how about this one? Let's give it a shot at 5 kilometers or 5,000 meters. What do we think it's equal to? Go ahead and pause the video and reason this one out. All right, so 54,000 pascals divided by 287 joules per kilogram per Kelvin times what we'd get here, about 255.65 degrees Kelvin. We can look here. You get about 0.736 kilograms per cubic meter. All right, well, I hope you did. So why is pressure such an important aspect of our climate? Well, the main reason, and one of the main reasons, is that differences in pressure, which are driven by things like topography and temperature, drive the flow of wind across our planet. That's where we're going next. We're going to dive into atmospheric wind patterns and how wind moves across the surface of our planet. So first off, let's talk about a fundamental scientific law. Air always flows from high pressure to low pressure unless something prevents it from doing so. It is pushed by a pressure gradient force, which is the change in pressure per unit distance. We can think of it as the difference in pressure between 2 points divided by the distance between those 2 points. So think of a soda can, right? The second you open it, you get that telltale whoosh or kind of sound, right? Well, that is what happens when the highly pressurized soda can is equilibrating to the atmosphere of lower pressure that you're opening it into. It's a high pressure and low pressure scenario, so it's rushing out of the can. That gas that's pent up there is rushing out of the can and equilibrating with the lower pressure atmosphere. So the vertical pressure gradient at sea level is equal to about 0.12 millibars per meter. So this means that the vertical pressure gradient on a cubic meter of air is about 12 newtons, which also means that the weight of a cubic meter of air is about 12 newtons. So this balance between the vertical pressure gradient force and the weight, so these kind of opposing forces, gravity pressing down, that parcel of air pushing up, is what we call hydrostatic equilibrium, which refers to the balance maintained between the force of gravity and the vertical pressure gradient that doesn't allow air to escape out into outer space. It's what maintains our atmosphere and keeps our atmosphere where we want it. So what is wind then? Well, wind is just air that's moving horizontally in the atmosphere. It's caused by the pressure gradient force pushing air from areas of high pressure to areas of low pressure to equalize the difference in pressure. So really, wind is just a horizontal expression of the differences in horizontal atmospheric pressure. We can see two maps here, one from the 2nd of March in 2020, the other from the 5th of March in 2020, with isobars denoting lines of equal pressure. So isobars are typically expressed relative to sea level pressure in millibars, which we can see here and here. We see a high pressure system moving west across the continent, while a low pressure system is moving southwest. So actually, let's go ahead and look at those systems in a little bit more depth and kind of identify some trends and names for some of the phenomena that we're seeing. So we can pick out a few certain features from these pressure maps. So for example, we call this low pressure system here and here a cyclone. So a cyclone is just an area of low atmospheric pressure characterized by rotating and converging winds and ascending air. The high pressure version of this is an anticyclone, which is characterized by diverging and rotating winds and subsiding air aloft. We'll look at these in a bit more detail in the next few slides. Next, we see this elongate low pressure system that we call a trough. Likewise, and finally, we see this elongate high pressure system that we call a ridge. We see that here as well. So pressure and the way pressure sets up across our, in this case, country or world really, is driven by elevation or can be driven by elevation and topography. If we look where the Rockies are, over New Mexico, Colorado, Wyoming, up into Montana and Idaho. And then we look here, we can see a high pressure system setting up right alongside the Rocky Mountains there. So let's look at a couple examples to look at the difference in the horizontal pressure gradient force. We're first going to look right here in the bottom portion of the map between the 1032 and 1036 isobars. So those are in millibars here. So the horizontal distance is 300 kilometers between those 2 points, which means if we do our math, the pressure gradient is 0.000013 millibars per meter, and the horizontal pressure gradient force on a cubic meter of air is 0.0013 newtons. Okay, well, how about up here? Notice how much closer these isobars are. Now let's think back to learning about topographic maps, right? If a contour line or a clump of contour lines is much, much, much closer together, is that a steeper slope or is it a more gradual slope? Well, we're going here from the 1024 to the 1016 isobars, a distance of about 200 kilometers, which yields a pressure gradient of about 0.00004 millibars per meter and a horizontal pressure gradient force on a cubic meter of air about 0.004 newtons. So in this case, that distance, that shorter distance with much closer isobar lines, has a higher horizontal pressure gradient force on a cubic meter of air and a higher pressure gradient in general. So next, we could ask ourselves what causes the differences in horizontal pressure across our world. So the primary causes are differential heating of the atmosphere, which we talked about in a previous video. These include things we call thermal lows and thermal highs. And then we also have changes in the speed and or direction of winds aloft, which includes dynamic lows and dynamic highs caused by convergence or divergence of winds in the atmosphere. So let's examine these and these causes in a bit more detail. So let's start by thinking back to the differences between cold and warm air masses. So recall that warmer air masses contain more excited molecules, causing the air mass to expand, leading to lower density within the air mass. Air molecules in cold air masses are not as excited and therefore are denser. So let's look here at about 5.6 kilometers in altitude. The 500 millibar level. So if this mass was warmer than the surrounding air, what would you expect in a thermal low pressure system? Well, that mass would be of lower density, so it would have expanded because of that warmth and excitement of the molecules. You would have a high pressure system aloft with winds diverging, so winds kind of moving away from the system. You would have a low pressure system at the surface with winds converging. And if we think back, recall that warm air, which is less dense, rises. Hence, we have rising air, which we can also see here in this graphic down below. So we've kind of got this system where winds are moving in and then up and then converging out. So you get this kind of cycle that's moving kind of away from the central position aloft and towards the central position near the surface. Okay, now what about a thermal high pressure system? So here we've got a colder air mass. What do we think would happen? So with this type of system, we have colder, denser air, right? So we would expect a kind of more compact air parcel. This means that there would be a low pressure system aloft with converging winds in the higher portion of the atmosphere. You would have a high pressure system at the surface because, that air is subsiding, it's denser, so it's sinking into the atmosphere. Warm air is rising, cold air descends. And we can see that here as well. So that leads to a high pressure system at the surface, what we call a thermal high, in comparison to its kind of counterpart, a low pressure system at the surface caused by high pressure aloft, warmer parcel of air, and rising winds, versus here where we have converging winds aloft, subsiding air, and surface divergence, so a high pressure system. So the pressure gradient force is one of the main factors affecting wind, right? We've talked about it now. It causes wind to blow, and the steeper the pressure gradient, the stronger the pressure gradient force, and the faster the winds. Now, the next major force affecting wind is the force of friction working against wind. So Earth's surface exerts a drag force in the opposite direction to that which the wind is blowing in. The strength of that drag increases as roughness increases. It also increases as wind speeds increase, and it decreases with distance from the surface. There is no friction force above the planetary boundary layer, which is basically the portion of our atmosphere that is affected by drag forces. So starting from the surface up to what we would call free stream, where winds are no longer being affected by surface drag. It's typically about 1 to 2 kilometers thick. So we can see here this exact thing expressed in the seminal work by Stephen Wolf and William Nickling in 1993. We see that in a smooth surface, wind increases rapidly until it reaches free stream velocity. However, when the surface is much rougher, for example, the presence of trees or buildings, there's a displacement in the bottom of the boundary layer to the top of that roughness layer. And we also see kind of a flatter increase in winds away from that surface. So it kind of trips up the boundary layer and causes it to slow down and become displaced upward. Finally, let's go ahead and talk about the Coriolis force. This is the force exerted on wind due to the rotation of the Earth, acting at a right angle to the direction of the wind. So wind doesn't cross isobars at right angles given this force from rotation. The Coriolis force does not itself generate wind, it modifies the direction of airflow. In the northern hemisphere, winds are deflected to the right of their path of motion. In the south, they're deflected to the left of their path of motion. Let's pretend that we can throw a ball with incredible force from the North Pole to our friend standing along the equator. All right. Here's us. Here's our friend. We are assuming that we're spinning kind of counterclockwise here. And there's our ball. So what happens, or what do you think is going to happen if we throw that ball? You think it's going to go right to our friend? Let's find out. So by the time you throw that ball, and by the time the ball gets there, the force of our spinning globe and the Coriolis force will have deflected that ball to the right. So we can see now the path that that ball is taking, and that's always going to be working at a right angle. The Coriolis force is always working at a right angle to that motion. We can see here, right? Here's our spinning globe. There is the North Pole, and we can assume that we are throwing that ball, and it's going to be deflected by that pressure and by that force applied by the Coriolis effect. Likewise, if we were standing at the South Pole and attempted the same thing, we would yet again miss. So here our Earth is rotating that way. Here's our ball. There's our friend. We missed. Ball is deflected towards the left this time. We can see our spinning globe here. Now let's look at a couple different examples. So here, if a plane was flying from Anchorage, Alaska directly towards Miami, Florida, would it miss its target due to the Coriolis effect? Yeah, it would. The target location where the plane was headed when it took off moved with Earth's rotation. So if the plane just flew directly at it, it would end up right of its actual intended target. A plane flying from Tierra del Fuego, Argentina, directly towards Rio de Janeiro, Brazil, would also miss its target due to the Coriolis effect. Here, if it flew straight towards it, it would miss its path to the left. You can see it skewing off course there. So the strength of the Coriolis effect, the Coriolis force, increases as latitude increases, and the strength also increases as wind speed increases. So let's go ahead and take a closer look at how these three forces impact wind cumulatively. So if we were to look at a molecule of air being moved by surface winds, the pressure gradient force is acting perpendicular to these isobars. The Coriolis effect is acting at a right angle to the motion of the direction of the wind, pushing it towards the right. This is a case in the northern hemisphere. The force of friction is pushing opposite the direction of motion. Okay, so as the pressure gradient force is stronger than the Coriolis force and the friction force, that molecule is being pushed from higher to lower pressure. The direction of the Coriolis and friction forces remain constant relative to the direction of travel. And then you also have still kind of opposing forces. So we're moving from higher to lower pressure, but we can see that we are being deflected. So there's still a force that's pushing against these molecules as it's moving towards the zone of lower pressure. And it's actually different if you're in the lower latitudes versus the higher latitudes. So this is probably a case where if we're in the higher latitudes, we would probably see something more akin to this, right? We're seeing a pretty broad deflection here. As a whole, winds would probably be moving in this direction in this scenario. If the strength of that pressure gradient force was significantly stronger than that of the Coriolis and friction forces, or if we were in lower latitudes where the Coriolis effect is playing a much smaller role, we would kind of see less of a deflection. Winds would potentially be something like this. In the case of a low pressure system, the pressure gradient force is towards the center of the system, the zone of lowest pressure, while the Coriolis effect leads to rotation of the system, and the friction force opposes that movement. We generally see this as a counterclockwise rotating system. So let's look at what that looks like in an actual map. Here, if you look at that big low pressure system centered over Wisconsin, we can see these bars. So the green arrows are the vector magnitude of wind. So the longer the arrow, the stronger the wind, and that wind is pointing in the direction that the wind is traveling. So we can see it's kind of this counterclockwise towards the center motion, as opposed to the higher pressure systems here, and they're kind of weaker high pressure systems that we see, but they're pushing winds out towards the lower pressure zones. Here's a really cool graphic from the website listed down there below of a low pressure system moving into the west coast of California. So this is kind of a cool one to see that counterclockwise rotation. This looks to be kind of MODIS or maybe one of the moisture satellites, and we actually see this zone of moisture spiraling in towards the center in a counterclockwise motion. In high pressure systems, we typically would see those winds deflected outward by the pressure gradient force in a clockwise direction. So, however, if winds are aloft, we can assume that friction force is not affecting the flow of those winds. So it comes down to just the pressure gradient force and the Coriolis force. Here, where air density is less and pressure is lower, the impact of the Coriolis force deflects winds more substantially, can actually come into balance with the pressure gradient force, turning winds parallel to these isobars. See here. That kind of looks like is what we see in this graphic here. When we look at winds higher in the atmosphere where isobars are relatively straight and evenly spaced, we often see winds flowing in roughly straight lines parallel to these isobars rather than perpendicular to them. These are called geostrophic winds, which are generated when a balance is reached between the Coriolis force and the pressure gradient force. If these winds flow from predominantly east to west, we call these zonal winds. Recall back to our definition of troughs and ridges, where these isobars form circular cells of either high or low pressure, what we would call a ridge or a trough. The isobars follow highly curved paths, and the winds flow roughly parallel, we can see here, to these curved isobars. These are actually called gradient winds, which result from the balance among pressure gradient force, Coriolis force, and centrifugal forces in winds aloft. These can lead to meridional winds, which follow a predominantly north to south flow pattern. So in this one, just to recap, we talked about what atmospheric pressure is, what winds are, and what drives winds, and what causes these horizontal differences in pressure and wind. In the next video, we're going to really dive into what these global circulation cycles look like, whether they are kind of the subtropical cells or where we see high pressure systems setting up over our world, typically where we see things like the Hadley cells or the intertropical convergence zone. So that's where we're going next. But I hope this was an informative video, and we will see you in the next one. Thank you.